Professor Deepak Chopra is currently a professor at the Department of Chemistry at Indian Institute of Science Education and Research, Bhopal, India. He joined the institute in 2009. He completed the integrated PhD program from Indian Institute of Science, Bangalore, in chemical crystallography under Professor Guru Rao in 2006, followed by postdoctoral work in the same institution till 2007. He further continued his postdoctoral work at the University of Toledo, Ohio, US, in the field of electron density analysis in molecular crystals under Professor Alan Pinkerton from 2007 to 2009. His active research interest includes investigation of polymorphism in drugs and pharmaceuticals, computational analysis of non-covalent interactions, in situ cryocrystallization, experimental and theoretical electron density analysis, and mechanical electrical properties in molecular crystals. He's currently on the editorial board of Journal of Molecular Structure, Cris and Com, and co-editor of Journal Acta Crystallographica E. Today, Deepak will talk on the role of quantum crystallography in the understanding of the role of weak intermolecular interactions involving organic fluorine. Please, the screen is yours.
Thank you. Thank you, Professor Paulina and Professor Christoph, for the kind invitation. And I indeed would like to express my gratitude to both of you for giving me an opportunity to discuss some of the work we have been doing in the field of chemical crystallography and utilizing quantum mechanical tools to understand weak intermolecular interactions, particularly those involving organic fluorine in molecular crystals. So, my study with organic fluorine almost goes back to more than 2 decades when we started looking at interactions involving organic fluorine. And before I go into the details of the problem, the first question we ask normally when we start in research topic is why would we like to work on a particular subject? So this is a slightly old slide, but the essence is the same still today. That we want to study fluorine-containing molecules because the applications are manifold, starting from agrochemicals to drugs to pharmaceuticals to liquid crystals, field of crystal engineering, understanding of the role of fluorine-based interactions in protein ligand assemblies, medicinal chemistry, sensing, recognition. These are some of the fields which have been benefited by the involvement of organic fluorine in crystal structures as well as in the solutions. Now, the challenge with fluorine is what the literature says, that fluorine is an atom which has got very high electronegativity. It is characterized by very high polarizability. It has got tightly contracted lone pairs. It is difficult to polarize the electron density distribution around fluorine, and therefore its participation in hydrogen bonding interactions is speculative. And this graphical image I took from the article of by Dr. by Robin Taylor, where he puts this fluorine atom, and you have got different kind of species which are actually in its vicinity. And fluorine is a bit confused because it wants to maximize the interactions, but what is more important is whether these interactions have the structure directing ability or not. And even if they are, what is the relevance of these interactions in the context of crystal packing? And this debate on the participation of fluorine as a hydrogen bond donor goes back to the early 1980s. And this is the first article, I believe, was quite authoritative when Jenny Glusker talked about the role of CHF hydrogen bonds, where in the last sentence it is mentioned that CF bond is capable of significant interactions with cations as well as with proton donors, although these are generally weaker than the corresponding ones involving the CO and CN groups. So this study was done in some specific crystal structures where they saw some contacts involving HF a bit around 2.29 angstrom, and 124 degree was directionality. So this was, I believe, a very important finding which kind of opened the gateways. Following this work, Simoni and Glusker published a database study which talked about the geometry of interactions in crystalline fluorine containing molecules. And we are talking about a time when the database was still developing and still large number of crystal structures were being determined and the database was getting populated. But we still did not have enough molecules to rationalize and generalize features involving intermolecular interactions, particularly those involving fluorine. However, in again here, she does mention that when you have CHF interactions, they are weak, much weaker than the traditional CHO or CHN, but they cannot be ignored in terms of their predictability of modes in packing in different complexes and crystals. So she does emphasize the importance of these interactions in the crystal packing. And then there was a this was followed by another article by another very popular crystallographer, Professor Judith Howard, in Tetrahedron, which kind of became a benchmark paper. How good is fluorine as a hydrogen bond acceptor? Again, this was a database study she performed, and what she wrote is these interactions are very rare, and it was proposed that when fluorine is connected to sp3 hybridized carbon, it is a better hydrogen bond acceptor than when it is connected to sp2 carbon. So these findings kind of followed and opened up the discussion on organofluorine based interactions. And then came the article by Professor Jack Dunitz and Taylor, where he talked about organic fluorine hardly ever accepts hydrogen bonds. And these were based on IPT calculations, quantum mechanical ab initio calculations, again taking very selected molecules along with from the database as well as from the PDB, where it talked about that fluorine rarely accepts hydrogen bonds. Again, I believe that the number of structures available were very, very limited in those days. Then, following this paper, in a short period of time, came a very authoritative article published by Professor Desi Raju Nangi and co-workers and Professor Boise, where he looked at CHF interactions in crystal structures of fluorobenzenes. Fluorobenzenes are molecules which are liquids at room temperature, so in situ crystallization was performed to determine the crystal structures, number one. Number two, what was also proposed is that there are some structures where the symmetry, the crystallographic symmetry is high. They crystallize in high symmetry space groups. So, what are the structure directing elements? And it was observed that these compounds contain carbon, hydrogen, and fluorine, and therefore CHFs are the basis of the crystal packing. And also, what was concluded in the end, which is very interesting, I believe, is that when you put fluorine atoms, you are actually enhancing the electronegativity of the hydrogen atoms. They are making them more acidic, and therefore they are more susceptible to participation in hydrogen bonds. So, if you have polyfluorinated system, then the hydrogens in the vicinity do get sufficiently acidic to participate in relatively shorter and maybe stronger hydrogen bonds to fluorine. So this was the essence of some of the very pertinent literature which came out. And then when I started my work as a master student, because the literature only mentioned about hydrogen bonds to fluorine in the absence of strong hydrogen bond donors and acceptors. So the group which I worked in, Professor Gurura's group, and some of my senior students there were actually crystallizing these kind of molecules like isoquinolines and tetrahydroindoles, which actually lacked a strong hydrogen bond donor, but which were actually having CF bonds in different positions like ortho, meta, and para. And the idea was to look at weak interactions involving fluorine. And these molecules did exhibit CHF hydrogen bonds, FF contacts, along with CHO hydrogen bonds in the crystal packing. And series of papers were published to exemplify that interactions involving fluorine are important and these play an important role in packing. And the summary of this work was we were able to detect and characterize some of the CHF hydrogen bonds, which were not very, very short, but nevertheless something like 2.5 angstrom, 120-degree directionality. This kind of a large size diameter was observed Then we also observed a very classical traditional CHF R228, the graph set analysis on this particular dimer, which is a very common synthon as proposed by Desiraju and co-workers. That this is a very populated synthon which comes in the crystal structures. And depending on what you functionalize, you can also have CHF here, where the CH is coming from the sp3 carbon, and on the other side, we can also have fluorines like CF3 instead of just a CF bond, where this fluorine is connected to sp3 carbon and forms CHF hydrogen bonds, and so on and so forth. So these kind of dimeric assemblies involving CHF hydrogen bonds only were isolated and characterized. So the next question was, can we have hydrogen bonds to fluorine in the presence of strong hydrogen bond donors and acceptors? And with that motivation, we started synthesizing these benzolides, which are very simple, relatively simple scaffolds to make, in the sense that just it's a one-step reaction, and then you have the CONH bond formed. It has a strong donor NH, it has a acceptor oxygen, and now you can template it with different fluorines on either the benzoyl side or the aniline side. And we were able to synthesize around 15 molecules starting from ortho meta para positions. And when we did the crystal packing analysis of these compounds, to summarize, some we saw some salient features. Most of the interactions involving CHF were between 2.6 to 2.7 angstrom and between 130 to 145 degree. And these were mostly secondary interactions which were trying to optimize the crystal packing. So we can see here that in addition to the traditional NHO hydrogen bond, we also have the CHF chains which connect the molecules. For example, in this particular orthoisomer, and then when we go to the disubstituted fluorine here, we have the NHO and the CHO supporting the formation. But in addition, we also have the CHF chain, and similar motifs or interactions set was also observed when we have a methyl group here in the para position, again having a similar packing pattern. And when we change the substitution pattern and we look at different molecules, for example, here we look at the para isomer on one side, we have again the NHO chain and the CHF interaction forming a sheet-like structure. So there is participation of fluorine in addition to strong hydrogen bonds in these crystal structures. Interestingly, in one of the molecules, which is the di-substituted para-substituted fluorine compound, so you see there's a fluorine on the para position on both the sides. You see this very interesting set of contacts. You see a twisted CHF dimer. You see a FF contact as a consequence of the CHF, and then on the top and the bottom you have another sidewise FF contacts. So these kind of contacts actually evolve in the crystal packing in this particular specific crystal structure. And further investigation on related molecules also showed the involvement of fluorine interactions along with strong hydrogen bonds. So this is something which was like a motivation to pursue this work further. And when you see these compounds in the solid state, then we were also interested to see that whether these interactions also evolve in liquids when we crystallize them. So we also performed in situ crystallization experiments on some fluorinated anilines. So in this case, we have the 2-fluoroaniline in the top and the 3-fluoroaniline in the bottom. The parafluoroaniline, as you can see here, it forms CHN and it forms CHF. Please keep in mind that there are no strong hydrogen bond in this structure. There is no NHN or NHF. It's purely weak interactions in a non-centrosymmetric space group PCA21. Contrary to that, the orthoisomer has got a disorder of fluorine, and there are 1.5 molecules in the asymmetric unit, so that makes it 12 molecules in the unit cell in the C2 by C space group. And here you can see the bifurcated nature of CH interacting with two fluorines in addition to NHN and NHF hydrogen bonds. So again, this optimization of the crystal packing, depending on the position of the fluorine, you have here both strong as well as weak, but in the para one, you only have the weak hydrogen bonds. So even when you are crystallizing compounds which are liquids at room temperature, they tend to engage in these hydrogen bonding interactions involving fluorine. So the next thing which came in our minds was to look at fluorine-based interactions with respect to FF contacts. And this was a challenge because primarily it was believed that atoms are spherical entities, but this particular article in Acta Christ in 1979 opened the new gateways, where it talked about the polar flattening concept, where you see non-spherical effective shapes of atoms in crystals. And subsequent studies illustrated these concept of polar flattening in heavier halogens, particularly iodine, bromine, and also in chlorine. But what we were interested to see is whether we can see the polar flattening in fluorine as well, whether fluorine also under the crystallographic environment, the crystal structure environment, is it possible to polarize the electron density distribution around fluorine? And what was proposed primarily are type 1 and type 2 contacts, where a type 1 context is essentially across the center of inversion, where theta 1 is equal to theta 2. But in the type 2 contact, it is this sigma hole region which interacts with the relatively electron rich region, and also referred to as the electrophile nucleophile combination, which forms these type 2 XX contacts. By and large, in the crystal structures, type 1 contacts were more dominant in comparison to type 2 contacts. So we were also interested to see whether we can have these features in fluorine containing molecules as well. So, so we undertook this experimental charge density analysis in two model systems, where we took one keto tetrahydroindole. These molecules have only one fluorine, so we want to see the specifics associated with one fluorine only, in the absence of any strong hydrogen bond donors and acceptors. And interestingly, this particular molecule crystallizes in P42 by N, which is a very rare space group for an organic molecule containing fluorinated compounds, and another molecule in C2 by C space group. And in specifically in the case of the the tetragonal crystal system, this particular phase, we see that there are four fluorines which come across the 4 to screw axis. So this forms a very nice tetramer, and experimental electron density analysis revealed the existence of the bond critical point, the bond part, and all the topological descriptors. Interestingly, this distance is slightly short than the sum of the van der Waals radii, and characterized by a positive value of the Laplacian. But we also see some effects of flattening of the fluorine atom. Particularly, if you see there is some distortion here, and there is some minimization of the repulsion, such that this region tends to interact with a slightly more polarized electron density distribution here. So there's some kind of attraction which exists, or minimization of repulsion between these fluorine atoms in this particular crystal structure. So this was kind of indicative that fluorine has a tendency to get polarized, as reflected in the Laplacian maps. And at that time, Pulitzer and Murray were also talking about the existence of the anisotropic electrostatic potential, the anisotropic electron density distribution around the heavier halogens, and a series of papers were published which talked about the possibility of the same feature being observed in fluorine as well. And this was reflected in these two articles. And this sequence, it's like a story. This is a sequence of events which are happening. And after we published, our charge density paper, then this paper arrived, where they say the fluorine atom is the halogen bond donor. That means you can have a positive side on fluorine. And then there was another article, Fluorine Centered Halogen Bonding, a Factor in Recognition Phenomena, where they showed the existence of FO contact in the crystal structure of a nitro trifluoroacetophenol. This work actually was done by us. We had published the in situ crystallization of the structure prior to this in CGND 2007, where we actually indicated this FO contact also to be present in the crystal packing. So now we see that not only FF contacts, but FO contacts also are relevant. And if it has to happen, possibly fluorine has to have the positive electrostatic potential. So this particular specific example was highlighted with respect to the possibility of fluorine being a halogen bond donor. And that was exciting for us, because now we started believing in the fact that fluorine can get polarized and can also have a sigma hole. So then we wrote this highlight in Christian's Com with my supervisor, where we actually summarized the findings of fluorine-based interactions, including the presence of the type 2 contact. And here we proposed that although it was already suggested that if you have electron withdrawing groups in the vicinity of a halogen atom, the electrophilic character or the sigma hole character tends to develop strongly. So we suggested the same thing for fluorine, that if you have electron withdrawing groups, for example, the carbonyl group in trifluoroacetophenone, as we suggested, you will be able to see the sigma hole character on the fluorine atoms. And we were not still very happy because there were still reports which were contradicting fluorine based interactions. And then we wrote this perspective, that is organic fluorine really not polarizable, where we tried to look at aspects of fluorine based polarizability and so on and so forth. So with this background, we were proceeding further. I was started my independent career initially with fluorine based work, and at that time Professor Guru Rao and Mysore Pawan, they published a very interesting finding in ChemCom, where they actually showed the first experimental visualization of the sigma hole on fluorine, a type 2 FF contact in this particular compound, which is a heterocyclic compound containing a thiazole moiety. And here you can see very nicely the precise positioning of the sulfur fluorine contact, where you can see the red region is the sigma hole, which points towards the valence shell, that is a charge concentrated region on sulfur. And on the other side, the fluorine sigma hole interacts with the torus of the electron density, which is the charge concentrated region. It forms a nice delta plus delta minus kind of a interaction in the 3D deformation density map obtained from experimental charge density analysis. So this proved unequivocally that fluorine is polarizable. You can see the sigma hole, provided you have some very specific environments. As you can see here, fluorine here is pentafluorinated. So it's highly polarized system in terms of the electron density, which actually resulted in the sigma hole along with the heterocyclic moiety. So this gave us confidence to go further into this field and explore fluorine based interactions. But what was missing is that can we see short hydrogen bonds to fluorine in the presence of strong hydrogen bonds as well? And that is something we started working on more molecules to characterize this. And these two papers, which I will discuss in the next few minutes, will actually highlight this feature better, where we looked at short hydrogen bonds to fluorine in molecular crystals, as well as the polarizability of organic fluorine in a trifluoromethyl group, which had never been explored before. So, with this, this is the first system I would like to discuss here. So now we make a molecule which has got both CF bond as well as CF3 group. So we have fluorine in two different environments. We also have a strong hydrogen bond donor and acceptor. This particular molecule A has two polymers, A1 and A2. A1 primarily has CH pi's, but A2 has got many short CHF's contact. And the other molecule B has got primarily the other molecule B here, where essentially you have interchange CO and NH, exhibits formation of very short CHF hydrogen bond. So these two specific systems, we were interested to look at the overall characteristics of weak interactions, CHF based, in presence of strong hydrogen bonds. I would again like to mention that one polymorph does not have many CHFs, mostly CH pi, but the other polymorph has many short CHF. So we can see that in the crystal packing now. So here we can see the NHO and the CHO mediated hydrogen bonding chains, and the chains are laterally connected by these relatively, I would say, not very short, but CHF contacts. It's 2.6, 137 degree is the directionality. And primarily the environment around this molecule is dictated by CH pi contacts, CH pi contacts. Whereas when you go to the other molecule now, as you can see here, there are two molecules in the asymmetric unit and they form very short hydrogen bonds. So out of the now total 8 fluorine atoms, because there are two molecules in the asymmetric unit and 4 per molecule, 6 of them are actively involved in the formation of short CHF contacts. And for example, this particular 2.32 angstrom, 162 degree, this kind of directionality and short hydrogen bonding length is observed now in the crystal packing of this particular polymorph of that compound A. So this is the first time you see such short hydrogen bonds. And now in case of B molecule, you can see here, this is the sheet-like structure. You can see here again, you get really short CHF hydrogen bonds, 2.23 angstrom, 173 degree. And in addition to that, you also have CHO, another CHF context by and large. And the NHO is also there, but it is perpendicular to the plane of the board. But by and large, CHF contacts along with short CHF contacts are here. So this was exciting because we were seeing very short hydrogen bonds to fluorine in the crystal structures. And then we first did the pixel calculation, and where we saw that the short CHF contacts have sufficiently high electrostatic contribution. So out of the total stabilization, around 50% is coming from the electrostatics if you had the Coulombic and the polarization part, whereas the other contacts are by and large dispersion driven. In the B molecule also, we saw the short contacts, relatively short and directional contacts. There also, we see the Coulombic and contribution is quite large. So again, telling you now that CHF interactions do have sufficient Coulombic contribution. Overall, the interaction energy is around 4 to 5 kilocal per mole, which is, I think, is slightly of higher strength than what was otherwise proposed for weak hydrogen bonds. So we are able to see this feature in terms of energetics. And now what we did was we wanted to analyze this further using different tools of quantum crystallography, particularly involving A-mol calculations. And at that time, already IUPAC had proposed some important criteria for hydrogen bonds. For example, cooperativity is very important, directionality and resultant influence on packing, observation of a 3 minus 1 bond critical point when you analyze the topological electron density distribution. And once you get the QTM analysis, as has been proposed by Koch and Popelier in their previous works, rho values must lie in this range. The Laplacian values must be greater than 0, and it must be in this range 0.578, greater than 0.758, less than 3.35 for the presence of a hydrogen bond, and the mod V by G must be less than 1 as proposed by Professor Espinosa. So keeping all these criteria in mind for hydrogen bonds and the characterization of disclosure interactions, we actually did a comprehensive database analysis where we did a search of HF hydrogen bonds less than 2.3 angstrom and greater than 165 degree in terms of directionality. And we got around 32 such contacts, and we did the QTM calculations. And then we plotted the rho as a function of Rij and the dE, both the V as well as the G as a function of Rij, the Laplacian. And there we were clearly able to demarcate that this is the region which is close to the sum of the van der Waals radii. These are short hydrogen bonds which are quite populated, and they follow the exponential trend. And also interestingly, that even for relatively longer HF contacts, these are topologically relevant and valid CHF interactions. So with overall this study now illustrates that short CHF hydrogen bonds do exist, topologically characterized, and these play an important role in crystal packing overall as well. So we cannot ignore CHF hydrogen bonds. And then we also wanted to look at the polarizability concept. So polarizability concept we wanted to explore, and now we took this specific molecule which has a ortho CF3 group, and this is the benzylide molecule, and we took another molecule for reference where there is a CF3 in the X2 position, followed by fluorine in this position. This is one of the molecules which have short CHF hydrogen bonds. Now, this molecule, the orthoisomer, interestingly has a high symmetry P41 crystallizes in this high symmetry P41 space group. You can see here the P1 screw axis, which connects via the CHF hydrogen bonds. And we decided to do an experimental charge density analysis. As we all know, it is challenging, but we need excellent crystals. So we were able to also get very good crystals for this particular molecule. And we collected charge density data to sin theta by lambda 1.1 angstrom. And after performing the multipole refinement, we also did the theoretical multipole refinement. The corresponding R factors are given here. The goof in italics, this is after the multipole formalism, and the residual electron densities as well. For the other molecule B, we did a theoretical multipole refinement to compare the electron density features between A and B. And again, this is a very important contribution to quantum crystallography, the development of the Hansen-Coppens multiple model. So we fitted the electron density to this model, and as you can see here, this is reflected in excellent statistics in the sense the probability plots as well as the scale factor variation over the entire range of sin theta by lambda is pretty fixed. It doesn't change too much. So we are confident that the overall quality of the model is high. The fractal dimensional plot was also okay, good. And so we proceeded now with the development of the charge density model for this particular molecule. And we can see here that the residual electron density reflects from experiment, it's almost featureless. These are the 2D deformation density maps, the static deformation density, and this is the Laplacian maps, which are pretty accurate. Here you can see that the CF bond is polarized, whereas in case of the benzene rings, you'd see a nice distribution of the electron density contours. Again, this polarization of the CF bond is reflected in the Laplacian as well. And after, so now we are happy that the model is good. We can now proceed with the topological analysis. So we now plotted the 3D deformation density map from experiment and compared it with the theoretical multipole. And now we see here very nicely the sigma hole on fluorines, three such sigma holes on the CF3 group. These are the charge efficient region. The charge concentrated regions are in blue. And we can also see that because of the extreme polarization of the CFT bond, the carbon atom here, as you can see, is highly electrophilic in nature, indicating that all the bonds are largely polarized. In case of theory, we see much cleaner maps in the sense that they are more spherical in nature. So we see again a similar distribution of sigma holes from theory. So this was, the eureka moment for us. We could see sigma holes on fluorine, and you can see the amount of polarization, the deformation is also large in case of CF3 group compared to what it was in the case of CF when it was connected to a benzene nucleus. And now things can be rationalized easily. We can now explain the formation of short CHF hydrogen bonds. As you see, the hydrogen approaches from the side where it interacts with the negative electron density distribution, the blue region. Similarly, we see another CHF contact approaching from a different region. This is in the A molecule, which crystallizes in the tetragonal space group. And then in the B molecule, we can see that very interestingly, FF contact, the sigma hole interacting with the charge concentrated region. So, contrary to what was suggested that FF contacts are repulsive based on DFT calculations, here from the multiple formalism, we can very clearly see that there is a polarization of the electron density and the sigma holes actually interact and orient themselves towards the electron rich regions. Again, the bifurcated nature of CHF hydrogen bonds to fluorine is also explained from these deformation density maps, which are obtained from experimental electron density refinement. So this now proves that FF contacts are realistic in crystals, CHF hydrogen bonds are also realistic. And it is the electron density distribution which plays a very important role in assembling these molecules. And to give you inputs on the data from the multiple formalism, the topological parameters we have for the for the relatively stronger hydrogen bonds, the values are high. But when we go to CHF, you can see that the electron density and the Laplacian values are appreciable. And we also compare the electrostatic contribution via the multiple formalism. The values are given here. These are obviously including the effects of polarization, and they are compared with the EML model. But the trends are similar, relative trends are similar. We see the hydrogen bonds, strong hydrogen bonds are highly stabilizing, and with increasing distance, the strength tends to decrease. And we can also compare these for the CHF. You can see 2.22, 2.44. These are relatively short CHF hydrogen bonds, well characterized, having a sufficient contribution in terms of electrostatics as well. So electron density analysis proves CHF contacts are important and stabilizing in crystal structures. And towards the end, I would like to give another very interesting example where we now looked at FO contact, side FO contact. So normally CF and CO dipoles are oriented parallel to each other. We don't expect them to interact much because there is dipolar repulsion. But interestingly, in this specific molecule, the 2-fluorobenzyl chloride, we saw a short FO contact, which is 2.64, which is quite short in the sum of van der Waals radii. And this is a planar system. The geometry is completely planar. And we wanted to actually understand what is the reason for this planarity. because the corresponding 2,6 compound and the corresponding unsubstituted compound are non-planar. That means the benzoyl moiety is rotated with respect to the plane of the phenyl ring. And we did a theoretical multiple model analysis here. These are liquids at room temperature, so we did the in situ crystallization. We got excellent data. So we proceeded with, based on the quality of the structure, we proposed to do a multiple model formalism. And here we can see that the carbon atoms are highly deficient. The fluorine and oxygen are electron rich, and therefore this is a nice example. This is a bridge like arrangement where we maximize the electron nucleus attraction and minimize the electron electron repulsion, which operates through these bonds and then even through space. So it is overall a coupling between through space and through bond effects, which very nicely supports this bridge like structure where the CF and CO dipole mutually come close to each other and form this short FO contact. This is the first time we observe such a short FO contact as well. So, and one last example I would like to give. We continue. We have been doing in situ crystallization also, and then see another very interesting molecule. This is a parafluoro trifluoromethyl. It is on the sixth position, 2 and 6, and this is the aniline moiety. There are two molecules in the asymmetric unit. We can see a NHN hydrogen bond, which is traditional, but we also see a FF contact in the asymmetric unit of a compound which has been crystallized in situ. Again, though you see the polarization is not significant, but nevertheless it is there. So we see this FF contact with the sigma hole orients with the blue region. And we compared the topological parameters from QTIM from obtained from AMOL with those obtained from the multiple formalism, and they compare quite well with each other. So topological data supports the relevance of these FF contacts as well. So So now to summarize, when we after almost 15 years of observations, Professor Robin Taylor published this paper, the hydrogen bond between NH or OH and organic fluorine, favorable yes, competitive no. I was a bit upset because none of our articles were cited in 2017, but in 2022, he wrote another article, Intermolecular Interactions of Organic Fluorine Seen in Perspective, where in the conclusion, he cited two of our papers, which I have discussed today, the perspective on challenging the polarizability of fluorine and the polarizability of fluorine-dependent trifluoromethyl, where he says that they have long been held to have low polarizability, although we have challenged this view. And now he accepts that it is not only occasional special circumstances, but it does have a significant effect on the intermolecular interactions in the crystal packing as well. So I've had email exchanges with him, and it has been a privilege to interact. And he has been very supportive of our work. And uh, I, I really would like to thank that he appreciated our work and contributions. And finally, to summarize, I would say quantum crystallography has been extremely helpful in unraveling the nature of organic fluorine. And I would now like to take a couple of minutes to acknowledge everyone who has played a very important role in this journey of organic fluorine, starting from Professor Guru Rao, my supervisor, and who, basically taught me crystallography. We learned crystallography. And his Professor K. Venkatesan, his supervisor, who was also visiting our lab regularly. So we had discussions with Professor K. Venkatesan. We had Professor Vijayan also that time in IIC Bangalore, a protein crystallographer. We also used to interact with him and learn a lot. Professor Pinkerton, my postdoc supervisor, with whom I learned a lot how to do challenging charge density and develop quality models. And my seniors who actually trained me, Dr. Anshuman, who is in Aisar Mohali, Dr. Munshi, who is in Shivnadar, Venkatesh, who is in Goa University, they all have helped me, in my work. And my students in 2009 to 2014, Piyush, Dhananjay, Abhishek, and Rahul, who contributed towards this field. And also to acknowledge the funding agencies. IIC initially, we had no machines. 2009 to 2014 was the year when we were developing a campus. We are just a 15-year-old institute, 16-year-old institute. So we had no campus, no buildings. We were only doing our research work in other institutes, thanks to my alma mater, IIC Bangalore, where I did all my research first few years. So, and then my own institute, National Research Foundation, Defense, DRDO, and ICDD for funding as well. And I would like to express my deep gratitude to all of you for being present for this presentation. Thank you all for your kind presence.
Thank you, Deepak. It was really very nice presentation and history of fluorine, organic fluorine discoveries. You can now post questions to the chat, and in the meantime, I have a question. Yeah, so you nicely showed us how quantum crystallographic approaches can help to understand all these interactions. But as you mentioned, you firstly need to have a good quality crystals and good quality measurements. And in case of your molecules, they are even more challenging, right? Because you have to do, in many cases, in situ crystallization. Can you tell a little bit about that? How long, for example, does it take to get one good crystal in situ?
Yeah, it is a very challenging thing. The time can vary. When we did these experiments, we did not have the optical heating crystallization device, which was developed by Professor Boise, which is CO2 assisted crystallization. We were doing all the experiments manually in the lab when I was a PhD student, and this used to take a lot of time. Sometimes it will take a day and you don't get crystals. We keep trying for months, we don't get crystals. So it is very frustrating and difficult, but somehow thanks to my seniors and we kept pushing the bars, and these fluoroanilines were the first two molecules we could crystallize after a lot of efforts. They tend to be glassy most of the time, but we were able to first determine the structures. Later on we had some idea about how to do these crystallization. We had some control, and later on we were able to get much better crystals, much better data, even data better than compounds which have good crystals, like in situ grown crystals. If you get really good ones, transparent high quality crystals, then the data actually can be very very good actually. But it's a matter of optimization, and once you are able to get the structure, we proceed for the theoretical multiple formalism, generate a theoretical structure factors, and then model the electron density. There was one case which I did not present, ethylene glycol, on which we actually did the experimental charge density of an in situ cryocrystallized liquid to look at absence of intramolecular OHO hydrogen bond in ethylene glycol. So that was even more challenging because that went for 5 days of data collection. So these are extremely challenging, time consuming, laborious experiments which are rarely undertaken today, actually. So my idea was to have different experiments to understand these interactions more and more, see whether we can also populate the database with more molecules, more structures, and competing interactions rather than not having participation of strong hydrogen bond donors and acceptors. So it is challenging to get very good crystals, and it is laborious. But doing charge density on in situ, I think, is difficult unless you hold on to that crystal for 5 days or 3 days or 4 days. Um, that way, theoretical multiple refinement is a very good tool which is available, provided you have high quality structures.
Talking about this theoretical multipolar refinement, Piero Macchi has a question or comment.
Yeah, I looked
Uh,
at Piero's comment. I think maybe that's a Piero is it's typed by mistake. Definitely, I by sigma is only for the experimental. Theoretical structure factors will not have because we generated. Yes,
And Hans-Bert Birgi, you showed a wide variety of interactions to and between fluorines. To what extent are these interactions determining the packing, and to what extent are they a result of imposed by the other parts of the packing?
okay, so yes, this is a very challenging question which we all have been trying to address. But towards the end, the molecules which I got, we have seen that NHO hydrogen bonds are even absent in some of the crystal structures. There are only CHFs and FF contacts, and they also take up the symmetry of the crystallographic symmetry corresponding to the space group. So, example, if you have PCA21 or if we have P41, P43, P42 by N, they do play a directing role in formation of different crystal structures, because without these interactions, I will not expect the formation of the three-dimensional structures. Number one. Number two, they are short contacts. Like I showed, some of the contacts are very short, 2.2, 2.3, and very directional, which was rarely observed. So fluorines, we believe, do exert their influence in these crystal structures. The third thing is that it is very difficult to get polymorphs, because polymorphs essentially means that you are able to play with the energetics and generate alternate arrangements by changing the energetics of very weak interactions, which you can change. But here, once the CHFs are formed, they tend to be quite robust and seem to dictate a very stable packing, such that large number of crystallizations don't really give us polymorph for most of the molecules actually. So I believe they do play an important role, and has also showed that from pixel calculations, some of them have got large electrostatic contribution also. And then because from multiple formalism also we see that they have sufficient role in terms of stabilization in the crystal packing. So cooperativity is very important in these fluorine-based interactions, and that is what I have observed. I mean to say, without these, I don't see how these structures would get assembled or get stabilized. Actually,
Thank you. And we have a question for Chris.
Hence, yes. So so yes, you actually this electron withdrawing effect manifest when you have multiple fluorines actually,
Hmm.
such that one region becomes relatively deficient and you have another region which is relatively electron rich or electrostatically more electron. Then there is a possibility of pi pi or CH pi. But in most of our structures, we have not seen much participation of pi pi, primarily because you have the strong hydrogen bonds and CHFs, which try to maximize themselves. And also the conformation plays a role here, the non-planarity of the conformation, which does not really allow for the close packing principles to prevail in terms of pi pi stacking. So
Hmm.
yes, it does have an influence. We have other papers where CF does influence the electrostatic potential, but it actually shows up with greater number of fluorines, so that you can see the effect of multiple fluorines on pi pi. So we have one paper where we have hexafluorobenzene in the crystal structure. It interacts with these kind of benzylides in a pi to pi fashion. But if you use
Hmm.
simply fluorobenzene, we don't get these crystal structures. So there is like a control here. You need to have sufficient number of fluorines to have enough deficiency such that they can stack reasonably well in the crystal and stabilize themselves. But
Huh.
then it's very sensitive to substituents actually, and effect on CHF hydrogen bonds per se together and then deconvoluting, uh, relative importance. I think at the level of crystal packing, I believe, Chris, everything is important, even the subtle interactions actually, like FO contacts. I did not present the FO contact
Hmm.
intermolecular. A slight offset, because it operates over the range of molecules in the packing, is sufficient to actually engage molecules, in a very dramatic way. Subtle changes in the electronic
Hmm.
distribution can actually influence contacts and crystal packing in a profound way. So
Yeah.
I think weak are also as important, if not, like strong, but relative strengths do play a role. And QTM does give us some answers in this regard. The topological criteria, even the pi pi stacking and FO contacts, proximity, distance, and so on and so forth.
Hmm.
But I think in a crystal packing, I think they all are important. I think so.
That's
All.
that's yeah. That's the unfortunate part. Is
That's a
everything's important.
yeah.
But in your estimation, a single fluorine probably doesn't have enough juice or enough electron withdrawing power to really affect the electrostatic
Yes.
distribution within say a
No.
conjugated
No.
molecule.
No.
Okay,
No.
okay, that's useful to know. Okay.
In fact, I would say when you have at least three, we have done large number. We have done more than 200 molecules
Yeah.
now, and we have another 200 in now still. But
Mhm.
we are actually, so what was suggested by Professor Desiraju, that when you fluorinate it extensively, you enhance the acidity to engage in CHFs to start with.
Mhm.
Okay, now you only have one single component system. If you really want to see its effect on pi pi, you need a donor, which is
Mhm.
relatively rich. So the classical example is benzene, hexafluorobenzene. And
Yeah.
we have papers where we have both in different molecules, And only when you have critical number of fluorines reach does this actually pipeline stacking start getting operational in a dramatic way, so as to influence the packing in a profound
Okay.
way.
All right. Yeah.
Yeah.
Krishna?
Some times ago, like, I don't know, 7, 8 years ago, we used to study by experimental charge densities fluoride, which is inorganic mineral, and we could have seen onset of fluorine bond. I mean, in general, covalent fluorine bond is one of the strongest, if not the strongest, bond in chemistry. But we could have seen in fluoride structure not
Yes.
interesting interaction between calcium and fluorine ions, but between fluorine anions, we could have seen a nice polarization of electron density, which was really, I mean, towards, directed towards the neighboring fluorine.
Yes.
That was really very nice to experience this very early moments of creation of bond.
Yes.
Fluorine.
Yes, 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 yes. I think maybe somebody can look at it. I don't know whether fluoride atoms, and then you have a proton in between or something else. Uh, how they can influence, the distribution and all. But I don't know there is much study done there. There are reports on CHF minus in sensing in a lot of literature is there. Supramolecular chemistry has a lot of papers on CHF minus fluoride and sensing, but I have not seen much work where a lot of crystallographic QTM analysis has been done, and still I think if you remember, Peter Luger was one famous guy who used to do in situ crystallization of. I did not talk about him. I also acknowledge him because I read those papers, very old papers, where that guy was actually doing in situ crystallization and charge density together, and he had already proposed so many things in those days, 1980s. So that was also compelled me that okay, I can do in situ crystallization and quantum crystallography tools we can employ wherever possible, if not
Because
experimental, at least.
I'm old enough to remember that time. Anyway, yes, I agree. These were very nice studies, and the whole system for in situ crystallization, the one proposed by Roland, who actually visited us plenty of time, and our colleague, Professor Michał Cyrański, is running one of such systems at our department. So that was very brilliant idea and brilliant setup, I must say.
Yes, yes. After that setup came, so when I started my career, we got that setup when I started my career here. So we have that setup now. We're still working after 12 years. We have done more than 30 liquids, and it's very challenging to keep students involved with in situ crystallization. They are not really involved with that kind of experiments because it's very challenging and arduous, and they take a lot of time with no results. So they are happy to do routine data collection rather than challenging charge density or in situ crystallization experiments.
Now, we would love to think that charge densities, experimental charge density studies would become like a routine studies, perform set of routine independent atom model crystallography. That's how it should be, I would say.
Yes, it should become more available and more, user friendly. In our days, it was difficult. I think now with the latest version released by Piero, it should become more accessible and people should practice using it more often, just like other tools we are using so often. That's it. The challenge is in the data, getting very good data.
Yeah, good. Yes, quality of the data. That's what really matters.
We are now trying to do tellurium and selenium based systems, and really challenging to get very good data because chalcogens are very well known in the literature. There's a lot of discovery with chalcogens, heavier chalcogens, but there's no systematic charge density study on the heavier analogues actually.
Deepak, in my opinion, crystallography has one ultimate challenge, which are hydrides of very heavy metal ions. superconductors, and that's we should attack.
That is the biggest challenge we have. Yes.
Okay, Paulina, can you see more question on chat, or because I do not see more?
No, there is no more questions. So let
us know then. Thank you, Deepak, for
Thank you. Thank you very much.
And for a very interesting discussion.